This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Good afternoon. So in the last lecture, we discussed about current mirror circuits and how to create current mirror circuits. So now what we are going to look at is how to get the current mirror implemented in an amplifier. So when you are doing a current mirror implemented in the amplifier, we will be seeing the notations like there is a current source I1, and then we are going to use a current mirror to bias this current source. So we have got two current sources here. Now how we can use the concept of current mirror to bias these current sources. So that is the reason we are starting from a problem. An integrated circuit, this is inside a chip. Integrated circuit employs source follower. So this is a source follower, similar to your emitter follower for BJT. Because this is a MOS transistor, this is a source follower. This is your input, and then your output is taking from the emitter. And a common source stage. Yes, this is a PMOS common source stage. And so this is an amplifier, this is a buffer. Design a current mirror that produces I1 and I2 from a 0.3 milliamps reference. So your band gap reference or the golden current is 0.3 milliamps. And then you got only one band gap reference, but then you have got two circuits. In the two circuits, you have got two current sources. So you want to use this golden current to bias these two circuits. So using one band gap reference, you have to generate two currents and then you bias these two current sources. So that is a question. Then that is not very difficult to do. This is a source follower and then this is a common source stage. So 0.3 milliamps, that is our golden current or the reference current. And then by looking at this one, MOS, you know that for this one, we can find out which transistor is required, NMOS or PMOS. Immediately we can see this is from a point to the ground. So point to the ground, so you need NMOS. Again here a point to the ground, so you need NMOS. So we know that these current sources, in order to realize this current source, we need NMOS. So we are going to realize the current source. Then we can use the current mirror concept. So I copy for the MOS, which we already discussed, that is equal to W by L 1 divided by W by L reference into I reference. But then for BJT, this is IS, saturation current of the reference transistor, saturation current of your transistor of interest, and then reference into I reference. So IS1 divided by IS reference into I reference, that is for BJT. But for MOS, it is W by L1 divided by W by L reference. So then what we will do is we will make a current source. So current source we already made using NMOS. So you can see two current sources. Then we are going to make a current mirror. So here is your golden current that is coming from the band gap reference 0.3 milliamps. So 0.3 milliamps is coming from the golden current source, that is your band gap reference, and then you are using this circuit current mirror configuration, and then you are using two NMOS, because here you need one NMOS for this one source follower and then one NMOS for common source stage. So you got two NMOS circuits, and then at the moment you got W by L, and then here when you have 0.3 milliamps, and then if you are using three MOS transistors in parallel, then what you will get is here you get a 0.1 milliamps. So very easy. Then in order to get a 0.2, how many you need? Here you need two MOS transistors connected parallel. In order to get a 0.5, here you need 5 MOS transistors connected parallel. So that is the reason we will be connecting here 2, then here 5. In that case, you get 0.2 milliamps here, 0.5 milliamps here, and the reference is 0.3 milliamps. So what we have done is golden current is 0.3 milliamps. You connect here 3 transistors in parallel, NMOS. So that is the reason we have written here 3 times W by L. And then here we connect 2. So 2 times. Then you get 0.2 milliamps. And then when it is 5 times, 5 numbers you connect in parallel, you get 0.5 milliamps. Then what you do is, now you got it. Now you can just connect this to here, because now you can replace this I1 with this M1, this part, I2 with this part. Because here from this point you need 0.2 milliamps. So that's the reason. So this part you can connect to here, and then this part you can connect to here in the chip. So that's how we will be biasing current sources. And then here we know that when we connect in parallel, for BJT we will be discussing about area, but then for MOS we will be discussing in terms of W by L. So that is the only difference. So here 3 transistors, when we connect for MOS, we are increasing the area, and then here we are talking about the area, because the saturation current area is the parameter you are increasing when you connect transistors in parallel, BJTs. For MOS, it is W by L. You are increasing the W by L. Again, that is area. So that is the reason here 3 times, 2 times, 5 times. And then that is the only difference between MOS and BJT current sources. And then because for the BJT, your saturation current, I copy equal to IS1 divided by IS reference into I reference, and then IS1 is proportional to area. But for MOS, I copy, which is equal to W by L1 divided by W by L reference into I reference. But the concept is same, because you are increasing the area. Then coming back to the example. So as I said before, so you already got a 0.2 milliamps here, then you just connect it here. So then now you got it biased. So see, now what you have got is, you got a current mirror, and then using that current mirror, you have designed the biasing for this current source and then this current source. See, so 0.5 milliamps is coming, and then when you do this one, you already got in a chip the golden current you are using for biasing your current sources, so that it is temperature independent, so that you can use in the chip. That's how we will be biasing. So when you have a current mirror, you have to design the current mirror, and then you should know how to connect this to the amplifier of interest, because that is very important. So you should be calculating how much current you are required here. Based on that, you have to design your current mirror, and then you design whether you need NMOS or PMOS, because this is a current source that is from point to the ground. That is the reason we have selected NMOS. So we got NMOS here, we got NMOS here, and the number is decided by how much current is required. Then you replace this I1 and I2 with these M1 and M2. So this is biasing. So now we know that how to create a current, how to design a current mirror, and then how to use that current mirror for biasing current source in the amplifier circuit. Similar to their bipolar counterpart, most current mirrors can also scale I reference up or down. Means we can apply same principle, whatever we applied for BJT, like scale up, scale down, we can use again the same principle to MOS, because this is applicable to transistor. We use the term transistor, not only limited to BJT, but it is applicable to MOS as well, all the current source principles. Only difference is when we use W by L instead of area for MOS, because MOS W by L is the term. So NMOS current mirror. So this is what we have done. So we have got a current mirror, and then we have used the current mirror for biasing one common source amplifier and source follower. So this is a source follower, and then this is a common source amplifier, and then this is a NMOS current mirrors. Then we can draw it as a general way, because this is with some number. Here you got a 0.3 milliamps golden current, and then here requirement is 0.2 milliamps and 0.5 milliamps. 0.2 milliamps for source follower, 0.5 milliamps for the common source stage. But we can draw it in general way. So whenever you have a followers, emitter follower or a source follower circuit, then you can do the biasing like this. So this is a general way of representing. So we are not putting any number here. So we got a golden current, then you got a current mirror, and then you got a source follower. Then we will be using NMOS, and then we will be connecting something like this. So you got a C common source stage, amplifier stage. Then again we will be using a current source here, and then this is a general way of representing without any number attached. So whenever we need a source follower or biasing, we will be using this scheme. So that's how we represent it as a general term. So we used NMOS current mirror here. So you can see NMOS. So that is a follower circuit, and then this is a common source stage in the previous example. Then now we have got, so this is a circuit in the amplifier. So you got a BJT. In the BJT you have got R1, and then this is a common. So what configuration is this one? Is a emitter follower, because here your input is here to the base and output is from the emitter follower. And then here what we will be doing is, here what do you need here? You need a NMOS, because then only you can make a current source. And then we will be connecting a constant DC voltage, because this is a signal you are connecting. And then here you will be connecting a constant DC voltage. This voltage will set the current. And then what we will be doing is, you use the current source, because here in order to bias this one, what we will be using is, we will be using the golden current. If you are using golden current, what we will do, this is a band gap reference. So the band gap reference circuit is, that is only one circuit, and then that will connect your VCC here, and then from that you will get the golden current, and then you make a current mirror, and then that current mirror will use for biasing this current source. So that, you know, here see, now you have got a emitter follower biased with golden current. So that's how we will be doing in the chip. So you got NMOS, you got NMOS first. Now I am showing you with the NPN transistor. So same principle we are using. But then when you have PNP, then you have a problem. Suppose you got your amplifier is like this. Here what you have done is, this is a common emitter amplifier. Then your load resistance is replaced with a current source in order to increase the gain. So in that case, this is from VCC to a point. So what transistor we need here? So definitely we need a PNP. So when you need a PNP, then we will be connecting a PNP here. So when you have PNP here, then we need a PNP current mirror. So when you make a PNP current mirror, so this is a PNP, and then when you make a PNP, we have to connect like in the PNP. Emitter should be connected to the supply. But then the problem is, then the golden current is coming down, and then it is going to the ground. So you have a problem, because when you have NPN, then you don't have that problem, because when you have this transistor, see, this is a transistor, then this is the current source. This is a current source, and then it immediately you can bias it. Then what you are doing is, you are going to make a current mirror for NPN. So when you are making a current mirror for the NPN, and then it is coming here, and then your base is connected to the collector, and the current is connecting to the collector. But then for the PNP transistor, what is the difference? For the PNP transistor, when you do biasing, you will be connecting supply to the emitter, and then drive this part, collector will be grounding, PNP. So when you ground here, then there is a problem. When you design a current mirror, then this is correct. So instead of this current source, you will be using a PNP. So when you are using a PNP here, then you have to use another PNP here, then only you can make a current mirror. So when you get another PNP, from the base you have to connect to the collector, then only you get to the biasing. But then emitter you have to connect to the VCC. But then the problem is, from here, then here you have to connect your golden current. You know what I meant? So you got a band gap reference here, and then can you connect your golden current to here? What is the problem? because this one is golden current is connecting to the ground. So whatever the connection you make it to here, then you are connecting to the ground. So we can't do that one. So then what we can do is, maybe I'll draw it and tell you what is the problem. So what is the problem is, so when you have this simple NPN case, so this is your current source, and then here what is happening is you can replace this with an NPN. So when you replace with NPN, then what you will be doing is you got one transistor here, and then another transistor here, and then this part, this is an NPN. Then we have to bias it. Maybe this one is requirement is maybe 0.x milliamps. So immediately then I want to use golden current to bias it. Then I will be designing a current source here, again using NPN, and then connect it. Then this is a band gap reference. So this is your band gap reference. This only one circuit. And then from that one, we will be connecting band gap reference coming, and then this is maybe your RC. So you got the power supply here to the band gap reference. Then for biasing this one, what I will do is from the band gap reference, maybe I will be taking another line that is a golden current. I can connect to this point. So that is my golden current is coming like this from the band gap reference. Now when you have PNP, the problem is, so you got your amplifier here. So at the moment now what is our problem is, this is your current source, this is your output. Then here you have to connect your golden band gap reference to this one. Then the problem arises because here you need what do you need? You need a PNP. Then you got your, this is a Q1. Then you got your Q1. Then you can connect to the ground, and then this is the output. But then when you have PNP transistor, you need PNP current mirror. So when you design PNP current mirror, again you need a matching transistor here. So you got a matching transistor, and then like here in the NPN, then you need your emitter to be connecting to the power supply because it's a PNP. And then you got your base, then you got the collector, but then the collector is connecting to the base, then only you can get a biasing for this transistor. But then the problem starts. For the PNP, this is going to the ground. It should be connected to the ground usually. But then you got this band gap reference. So here also you got the band gap reference. So this is your only band gap reference. And then the band gap reference will be connecting here for the power supply. But then for biasing this current mirror, you need to connect current here. But then you can't connect current here. If I connect current here, what is happening is you are shorting my point to the ground from the band gap reference. You know what I meant? So you can't connect it. Then what you will do? Then what will you do is you have to design another NPN current mirror. Because here, when you look at it, maybe you can connect here one point to the ground so that you can connect an NPN transistor. When you have NPN transistor, then we will design another NPN current mirror. See? So when you have PNP current mirror, because we can't connect your golden current to this point, because this is a golden current, we can't connect it because then this is ground. You are grounding your band gap reference. In order to avoid that one, we will be using a NPN because this is from point to the ground, we can replace this with another NPN. And then we design a current mirror for that one. Then that point you connect to the golden reference so that you are not connecting to the ground. So when you have PNP transistor, you need NPN current mirror. So that is a bit complicated. So PNP is always expensive to use because when you use PNP, then you need NPN. So PMOS current mirror, and then so in order to represent in a general way, if you are not putting in any number, so this is the current source, you want to bias it. So then you will be using a PNP transistor, and then you will be designing a PNP current mirror. But then PNP current mirror, in order to bias that one, we need another NPN current mirror. So this is a common source stage and follower stage. Then if you want to bias it here, now the arrow is here is load resistor is here. As I said, we need PMOS. Then here also you need a PMOS. So that's the reason here now we are replacing these currents with PMOS, pretty much like this. And then we have to provide another PMOS transistor for current mirror. Then you need another NMOS current mirror to bias your PMOS current mirror. So if this is the case, so this is a common source amplifier. Now what we are doing is we are replacing the load resistor, and then here also we are doing the same thing. We are connecting V input here, and then we are taking output from the source. Then what we need is what we did before for BJT. So you got PNP, you got PNP, then we got a PNP current mirror, then we use a NPN current mirror for biasing the PNP. Same with the MOS. In the MOS, this is a current source, so that you are getting a PMOS, and for this one also you are getting a PMOS. Then we connect together because we want to make only one current mirror for the both, for biasing both. Then you connect together. So this is the one. So this I1 you replace it with a PMOS. This I1 you replace it with another PMOS, and then you connect together. Then you will be having another transistor, that is the PMOS current mirror part. Then because this PMOS, ideally you should connect your current, golden current here, but we can't because here it is connecting to the ground. So that we will have another NMOS current mirror to bias this PMOS. So that's how we will be doing. Similar to our PNP configuration. So PNP, we replaced the current source with the PNP, then we got a PNP current source. Same with here, see, PMOS. Because here you got two circuits, here you got only one circuit. And then two circuits we connected in parallel, and then we used a PNP current mirrors. Sorry, an NPN current mirror. So here you will be using NMOS current mirror. And then NMOS and PMOS. So this is a PMOS current mirror. Then you got two amplifiers. Because here this is your input, here this is your input, this is an amplifier stage, C common source stage, and then this is a follower stage, this is a buffer stage, and then here the load resistance we are replaced with the PMOS, here also we replaced with the PMOS. Then we got a PMOS current mirror, and then PMOS current mirror we use NMOS current mirror to be a bias PMOS current mirror. Then we got NMOS current mirror. In the NMOS also we did the same thing, and then we have got a follower and then common source stage from the example 1. In the previous example, then what we did is that time we replaced the current source here, and then that time we replaced the current source here, and then here it is pretty simple because it's an NMOS. Then you need only an NMOS current mirror. You know what I meant? With this problem we already did it. This problem, if you check it, see, this is what we did it. So first our problem was here, this one we replaced with current transistor current source. This also replaced with the transistor current source. And then here we used the NMOS. We need NMOS. So that was easy because you got a NMOS transistor here, NMOS transistor here, and then you can bias, you can connect together, and then you can vary the number here depending upon how many transistors, how much current you need. You can connect transistors accordingly here and here. So that's the reason we can connect parallel, and then you can connect to a NMOS current mirror, and then you connect the golden current here. So that was easy because this is from point to the ground. But then the previous case, what is happening is now what we have got is other way around, because now we are talking about this current source. Because when you have this type current source, that is from a VCC to the point, VCC to the point. So you need a PNP. So when you have PNP current mirror requirement, then that is difficult because you need another NPN current mirror to bias the PNP. So PNP current sources are always expensive in terms of number and in terms of power requirement. So if it is NPN, that is easy. So PNP means you have a problem because PNP, this part is grounded, but then you cannot connect golden current here. So that is the reason you need another NPN to bias it. And then in the chip, when you are designing a chip, what you will find out is you will have so many PMOS so many NMOS current mirrors, because you may have these type current sources. See, this is a pretty common in the chip design, because this is an amplifier and then your load resistor is replaced with a current source. Then this is a follower circuit, a buffer circuit. Here also PNP, and then the load is replaced with current source. And then in order to replace this current source with a transistor, you definitely need a PMOS. Here definitely you need a PMOS. And when you have PMOS, as I said, you will be designing a PMOS current mirror, and then PMOS current mirror you will be connecting again to NMOS current mirror for biasing it. And then when you design chip, you have both. So you have PMOS current mirrors, and then you have got NMOS current mirrors. So when you design the chip, the problem is you should be able to combine both. Combine both means you got only one band gap reference, and then you may have PMOS circuits, PMOS based amplifiers, NMOS based amplifiers, or PMOS transistors in the design, or NMOS transistors in the design, or PMOS current sources, NMOS current sources, but then you don't want to have separate connections. So if you look at this PMOS current mirror, this part is NMOS. If you do NMOS current mirror, this part is NMOS. You know what I meant? Then what I will do is I can knock off this part, and then I can connect this point to this point, so that I can get rid of this one. You know what I meant? Because this is common in the PMOS current mirror and the NMOS current mirror, then this part is common for both, so that we don't need both in the design. And then if you connect it like this, it is called a CMOS current mirror. So NMOS plus PMOS, that is called a CMOS. So that's how in the CMOS circuit they will be doing the biasing. So in the CMOS circuit, an example, you have got 4 amplifiers. And in the 4 amplifiers, one is a common source stage amplifier. Here you are replacing this load. Another follower that is based on here is a PNP or PMOS. Here because the MOS, so it's a PMOS, and then here you are replacing a current source with a PMOS circuit. But then this is another follower, you have used the NMOS circuit, and then here the load resistor you will be replacing with the NMOS transistor. Again, this is a common source stage, and then in the common source stage here you are using a PMOS, and then but here your load, this load is here down, and then you are replacing with the NMOS transistor. But then when you have PMOS, then you have a problem. You need an NMOS for biasing. But then for NMOS, that is pretty simple. And then what you do is here this stage is common for PMOS circuits and NMOS type circuits. So we will use only this mirror, and then this part we will be connecting to your band gap reference, this current. And then from the band gap reference it is coming, and then this will mirror the current, and then depending upon the number, how much current you need it. So you can connect maybe 2-3 transistors in parallel, maybe 2 transistors in parallel. Here you can include maybe 1 or 2. Again, here you can connect to 2 transistors or 3 transistors. Here you can connect to 3 transistors or 4 transistors, depending upon the current requirement. So here you will be mirroring that current here, and then depending upon the number that you are using here, how much numbers you are putting in here, you can match your requirement. Means here maybe 2 milliamps is coming, but then for this one your requirement may be 6 milliamps. Then you can connect maybe here how many? Here 3 more you can connect it. Here you can connect another maybe 3 more, 6 milliamps. Here if it is 4 milliamps, you can connect 2 in parallel. So if you need a fraction, then what you need is either you can adjust here or you can adjust here. If you need adjustment only for PMOS, you can connect some transistors here in parallel so that you can scale down the current here. But if you want scaling down for NMOS part and PMOS part, then you can connect here as well. So that's how. So when you have a big circuit, I will show you in the coming lecture, when you have a big circuit, you can actually find out what is the current flowing through maybe one amplifier stage. It is just simply some maths, because you know how this will be mirroring, and then if this is 0.2 milliamps, you can find out what is the current here in each branch, and then we can exactly tell what is the current maybe flowing through this circuit, or maybe this part, what is the current. We can actually find out. This is very simple to write it. I will show you some examples in the next lectures. So that is a PMOS part, and then that is a NMOS part. So when we connect NMOS and PMOS part together, we got CMOS. So that's how we will be using CMOS. The idea of combining NMOS and PMOS to produce CMOS current mirror is shown above. So that's how in the chip we will be doing the biasing. And I think that is a current mirror. I think maybe we will be finishing current mirror here. And then one more section is left, that is short circuit transconductance. So that we will be studying in the next lecture. And then also I will be looking at some of the small problems like how to get the current. That I will discuss. And after the mid-semester test, we will be starting a new section, that is a differential amplifier. So in this section, what we studied is current source, how to increase the impedance of the current source. We came up with the idea of cascade stage. Then we studied a cascade amplifier. Then we studied the importance of current mirror. Why do we need a current mirror? Then how to design current mirror. Then how to design current mirror and connect to amplifier to replace the current source. So these are the things we have studied. And then the one that we left is short circuit transconductance. So short circuit transconductance, you might have seen in the textbook. I think maybe it will come in the middle of this current mirror chapter. So short circuit transconductance means that is people call it as a lemma or a method to find out the gain. So why do we need a short circuit transconductance? Anyway, we will start in the next lecture, but I will give you a simple example. So what is a short circuit transconductance? So as I said, it's called a lemma. Oh, sorry. So it's called a lemma or a technique or a method. And then why do we need a short circuit transconductance? So it is called a short circuit transconductance. So that's or you can call it as a method to find out the gain. So from the small signal, you can find out the gain. But then this is another technique. You can find out the gain. Then why do we need, what is this short circuit transconductance? Short circuit transconductance is when you have an amplifier, then you have to find out the gain. Then what the method is, this is your output. And then they will draw the small signal. So again, you need a small signal, but then what it says is you draw the small signal, this is a V in, and then this is your RL, so this is your RL. Then short circuit transconductance means it will short the output. Then we'll assume that some I current is going out into it, I out. You know what I meant? They short the output and then assume that some current is going inside. And then they will find out this I out divided by V in. So what is I out by V in? Transconductance. So then you got the transconductance. Then that is a number one step. Then in order to find out gain, you need transconductance into something else. Transconductance may be GM into what you need? R out. Then what they will do is they will remove this one and then connect. In the second part, what they will do is you got the same circuit. This procedure you already know. Then what they will do is you got the RL. Then they connect a test voltage source. Vx, Ix current is going, and then they find out R out separately. So you find out transconductance separately, R out separately, and then multiply together, you get the gain. So that's called short circuit transconductance method. So some students like this method, some students like just finding directly, gain from the circuit. Then what is the relevance of this short circuit transconductance? Why people are doing this one? An example is the following. The short circuit transconductance will be easy to solve the circuit when you have so many transistors. So my question is, this is your V in. Then I am going to connect it from here another transistor. And then maybe I connected here to some voltage. And then this both I am going to connect to some emitter of the transistor, some VCC. It's a crazy. Then this is output. Then from here I am getting another transistor to the ground, maybe this VB, and then this is the V out. So you got Q1, Q2, Q3, Q4. Then if this is a circuit, and just an example, this might not be a working circuit. So when you have a complex circuit like this, then you will ask which transconductance will be contributing to your gain. So then here we can say, I can write the gain equal to capital GM into R out. So capital GM means that is a total transconductance of the circuit. That is a function of GM1, GM2, GM3, GM4 to GM4. You know what I meant? So if you can find out total transconductance, then you can find out R out. Connect a test voltage source and find out R out. Then we can find out the gain. Then that is the reason in the short circuit transconductance, we will be shorting the output and then saying that I out is going in. So that your I out by V in, when you are finding out I out by V in, then you are getting actually capital GM. Why? Because this current is going in and contributing to all these transistors affected. So that's the reason that output is shorting, and then we are finding out I out by V in. Then this technique is definitely useful for some circuit, like a complex circuit. You need a small signal, but the small signal, just by small signal itself, sometimes we won't be able to get the answer. Maybe this is the quickest one. Because when you do this short circuit transconductance, I can show you in the next lecture, in the next coming lectures, when you short this one, there are many sections that will go away in the circuit. It will become simple. Because your output is shorted, then some other areas, if you got a ground, then between this ground and that ground, no current, so that your circuit will collapse. But then, not always, in some circuit, complex circuits. So that is the idea of a short circuit transconductance. So that is a lemma. In the textbook, they call it as a lemma or a method or a technique to find out a short voltage gain. So you can also use this technique for finding the voltage gain. So I got a big printout with lots of derivations, some complex circuits. And then I will post it on LMS after I teach you this short circuit transconductance. I will take a couple of the examples and I will derive it in the lecture. During my lecture, I will derive it so that you will get an idea. Because once you get an idea, you can do it by yourself. And then for the exam, if there is a question, find out the voltage gain of the below circuit. Then you are welcome to use just a small signal or short circuit transconductance. But if the question is find out the gain of the below circuit using short circuit transconductance, means you have to use this technique. Then you got two tasks: find out the capital GM and then find out R out, output impedance. So usually we ask a question from the short circuit transconductance. I'm not giving you what is in the exam because we got a fixed pattern for the final exam. So if you take your last year final exam, the year before, you can see some pattern. So there is no trick. We have not tricked you. So you can find out there is a pattern. In some particular current mirror, we will be asking questions. Differential amplifier definitely will be asking questions. All the sections we will be asking questions. You can find out a pattern. Means why we provide that pattern is we will not trick you. Means if you understand that one correctly, you will get the mark. That is our intention. But then the questions will be tough. Some of the questions will be definitely tough because we don't want everybody getting H1, because only those who understood very well. Having said that, ECD, I think last year we got, 23 or 24% H1s. Means a lot of students did really well. In contrast to my another subject where we get only like 13% ESD. Yeah, so you will find out there is a pattern. So operational transconductance is a technique that you should be mastering, because then you will get much more understanding in the small signal. Then you might, so we have two contrasting cases. In the lab, you will be using lots of discrete components and using small signal analysis, but then still we are linking with the small signal analysis. Because after this subject, I don't think you will be learning any small signal for the entire duration. Because then why do we need a small signal is when you are designing, maybe some of you designing chip or some of you maybe mastering in electronics, this knowledge is very important, the small signal. Especially if you are doing chip, definitely you will be starting from the small signal and then up. Because we do cadence chip design in my group. So this is kind of very fundamental. If you don't know this one, you can't design the chip. Plus even you will get a much better insight into the circuits. And I will stop here and see you for the mid-semester test on Thursday.
What time should we add the channel modulation, channel length modulation to like 1 plus lambda VDS when calculating the ID? Because for the most quiz, for question.
Yeah, so there is a question, we haven't taken into account lambda, I know what you meant. Because the equation you need 1 plus lambda into VDS, but then we don't know the VDS.
Yes, so we need to use VGS to represent that.
Yeah, so because we don't know the VDS, we haven't taken into account the 1 plus lambda into VDS term in the quiz. Maybe that is a question you are asking, isn't it?
Yes, like for question 7, you add it. You use this.
Yeah, VDS. So what did you do for the VDS? What do you substitute?
Equals VGS.
Yeah, it's
Okay.
But in like question 30, you did add it.
Yeah, so for the question 13, so where is the question 13? Yeah, the question 13, no way we can come to know, what is VDS.
Yeah.
You know what I meant? Yeah.
So
Yeah, for the question 13, we can't find out VDS.
ECD，另一个 ECD，没有 ES。